extending the idea of inference on a single population proportion, let's look at two population proportions. And this is a common situation, in particular, where you would like to compare the two binomial parameters. And the notation we're going to use for these two parameters are pi1 and pi2. In particular, we assume they're unknown, as is reasonable. We take samples from these two underlying populations, and we have y1 successes from the first sample of size 1, and then we have y2 successes of the second sample of size 2, and from that we form our point estimates. Okay, and so here's our 2 point estimates here. Pi1 hat is simply the number of successes from sample 1 divided by n1, and pi2 hat is the number of successes from sample 2 divided by n2. Okay, so what we want to do here is ultimately interval estimation and hypothesis testing. The assumptions in order to go forward with that are as follows. Well, before we get to the assumptions, let me say something about how we compare these two proportions. Typically we look at the difference between the two, and that's pi1 minus pi2, and we look at the difference to do a comparison. Now you could look at the ratio, and there's a technique for that, but for now we're going to consider the difference between the two population proportions. The difference of the sample proportions is a natural point estimator for the difference of the population proportions, and so we ask the question, what is the sampling distribution of this point estimator? Well, it turns out that pi1 hat minus pi2 hat is approximately normal, and the mean is given by this expression here. That is, the mean of the difference of the sample proportions is actually the difference of the underlying population proportions. Okay. And the standard deviation of the difference of the sample proportions is given by this expression here. So what I have are the pieces for the sampling distribution of pi1 hat minus pi2 hat, and I can go forward with some inference. Now, the normal approximation to the distribution pi1 hat minus pi2 hat requires large samples, and this is the rule of thumb for a large sample in this situation, that for both samples we have the sample size times the probability of success is at least 5, and also the n times 1 minus the probability of success is at least 5 as well. So that has to happen for both samples. That's our rule of thumb there for a quote-unquote large sample, and apply the normal approximation. Now, the confidence interval looks like a lot of the other intervals we've had. What we're going to do, actually I may make that clear, it's the point estimate plus or minus the z percentile times the standard error. Okay. Now I need to, for some reason it hasn't showed up on the notes here. I'm looking at it, it's not showing up right. This should have a hat on it. I'm estimating that, and here I've got the sample estimates for pi1 and pi2, so you want to make that adjustment. I don't know the underlying proportions. If I did, I would not be estimating their difference, but here we replace those with the sample statistics. Okay, that's the regular confidence interval on pi1 minus pi2. An adjusted interval on pi1 minus pi2 is similar to the adjusted interval on the single proportion that we saw earlier. We add 2 successes and 2 failures to both samples, and that's reflected here. Okay, and we'll apply this in an example in a little bit. Okay, so here's our example. So take a moment, read this example. You may want to hit the pause button, get your bearings. Alright, so hopefully you've read the example, and what we want to do is we wanted to compare the proportion of consumers, or really the difference of the proportion of consumers who are aware of this product between the two regions here. And so I'm going to up front define the parameters of interest. Okay, the parameters of interest here, pi 1, would be the proportion of all Grand Rapids citizens who are aware of the product. Okay, and then pi 2 is the proportion of all Wichita citizens who are aware of the product. And so we're interested in comparing these two proportions because the two methods of advertising are different here. Is there a difference? Do we see a difference in these two proportions? And so what we want here is we ultimately want a 95% confidence interval for pi 1 minus pi 2. Okay, and we'll use the adjusted formula that we had on the previous page. So we'll use pi 1 tilde minus pi 2 tilde plus or minus a z percentile times, again, the estimated standard error. And instead of that entire square root term, I'll just write out sigma hat there. Okay. Now, from the data, what do we see from the data? What is my sample estimate of pi 1 under this adjusted approach? Well, dealing with Grand Rapids here, I'm going to have y1 plus 2 over n1 plus 4. There was 392 people out of the Grand Rapids survey that were aware of the product. So I have 392 plus 2 in the numerator there, and then in the denominator I'm going to have 608, that's the total number that were interviewed, plus 4 there. Alright, and so if you do the arithmetic there, you get 0.644. Doing a similar approach, computation for Wichita, that's y2 plus 2 over n2 plus 4. It's going to be 413 out of that survey were aware of the product, divided by the sample size was 527, then add 4 to that. We have 0.781. Okay, so here our confidence interval then, our 95% confidence interval for pi 1 minus pi 2. Alright, we're going to take here the point estimates, 0.644 minus 0.781, then add and subtract the z value here. Hopefully you've done enough problems where you know that the z score associated with 95% confidence is 1.96, but you could look that up if you need to. Okay, and then times the square root term, or this standard error of the difference of the sample proportions. That's going to be 0.644 times 1 minus 0.644 over n1 plus 4, which is 608 plus 4. Then plus, now everything involving the second sample here. Okay, so I'm going to have 0.781 times 1 minus 0.781. Divide that by 527 plus 4. And if you do take the difference here, you have negative 0.136. Okay, now that's my point estimate for the difference of the population proportions. Alright, so that's my point estimate. I'm going to add and subtract this margin of error to get my interval estimate. It turns out if you do that arithmetic, and that may take you a couple of steps there, be careful that you do the ratio, this ratio first, and then add it to this ratio, and then take the square root. Okay, so get your order of operations correct there. And if you add and subtract that margin of error, you get a lower bound of negative 0.187 and an upper bound of negative 0.084. Alright, so this is a 95% confidence interval on pi 1 minus pi 2. So what does this suggest, and how do we interpret this? Well, it might be a little tricky when you look at it first that the interval on pi 1 minus pi 2 has negative values in it. Okay, well, we know proportions can't be negative, but their difference can be negative. Okay, so what this is saying, if the difference is negative, that suggests that the second proportion is larger than the first proportion. In particular, that it could be larger than the first proportion by as much as 18% or as little as 8%. Okay, and so we want to reflect that. So let's interpret this confidence interval here. Okay, so we would say we are 95% confident that I'm gonna word this in terms of the larger proportion compared to the smaller one. So we're 95% confident that pi 2 is larger than pi 1, and it's larger than pi 1 by at least 8.4% and by at most 18.7%. Okay, that's how we interpret the interval on pi 1 minus pi 2. And so what that would do is that might suggest that there's a difference between the awareness, customer awareness in Wichita and Grand Rapids, that it's greater in Wichita than it is in Grand Rapids. And so the marketing company may conclude that they might conclude that that particular mix of advertising techniques is better. Okay, and so that's an inference that they could make. It turns out that proportions could actually be different for another reason, that they could be different, that just regional differences between those two cities there may be driving the difference in the proportion of awareness. But anyway, that's an illustration of a confidence interval on pi 1 minus pi 2. We can also do hypothesis tests on pi 1 minus pi 2, and we can do, in particular, we can do 3 kinds of tests here. And so we can check to see, is pi 1 minus pi 2 negative? In other words, is pi 2 bigger than pi 1? We could check to see, is pi 1 minus pi 2 positive, a right tail test. That is checking to see, is pi 1 bigger than pi 2, or we could just check for a difference between the two proportions. And the test statistic you're going to use here is a z-test statistic, and it's pi 1 hat minus pi 2 hat divided by the standard error estimate of the difference of the sample proportions. Again, you're going to use this when the rule of thumb for a large sample size or large sample sizes are appropriate here. Okay. Like I said, in the single population proportion case, I prefer to use the interval to perform a hypothesis test, and that's my preference here as well, although we need to be mindful that you could use this test statistic to do any of these tests here, and that hypothesis testing does have its role in comparing two population proportions. Okay, so this brings us to the next section, inference for several proportions.